10.3, example 6. In this example, we're going to look at how to find the area when working in polar coordinates. So recall from geometry that the area of the sector of a circle is 1/2 r squared times theta. The idea here, if you remember back to a circle, the area of a circle is pi r squared because theta is 2 pi, and then 2 times the 1/2 gets rid of the constant. So then, where r is the radius and theta is the central angle in radians, or that's how much you revolved since your original point. So if we just take this idea and go a little bit further, we can get the area of a polar curve is the integral from alpha to beta. Instead of a to b, we use alpha and beta because we're talking about angles, and 1/2 r squared d theta, because r is a function of theta. So you can also think of this as 1/2 the integral alpha to beta of f of theta squared d theta. So basically you want to get your function, square it, and then integrate it, and alpha and beta represent the first theta value and then the last theta value. So in example 6, we want to find the area of the region that is enclosed by the function r is equal to 2 parentheses 1 plus cosine theta. So I've gone ahead and I've broken this down into a couple steps. So step 1 is to look at the graph. So what we're going to want to do is go ahead and graph this on your calculator and take a look at where this thing starts and where it ends. Alright, so I'm going to go ahead and graph this right now. So as I trace it out, I should get this shape. Kind of looks like a little dented heart. And notice that to go from start to finish is 0 to 2 pi. So it goes from 0, and then it's going to go all the way around until it gets to 2 pi, which is when it closes its shape. With polar functions, you want to go from when the shape opens to when it closes or connects with itself. So if I fill that in, the idea is we're going to integrate to find the area inside of this curve. So after you have this graph in your notes, it's a lot easier to see where you have to start. This starts at the point 4, 0, where this is r and this is theta. And then it's going to end at 4, 2 pi. Again, this is r and this is your theta. So step 2 is to go ahead and set up the integral. Alright, so when we set this up, we're going to have the integral 1/2 alpha to beta, our function in terms of theta, squared d theta. That's our equation. So it's going to be 1/2 the integral from 0 to 2 pi, and my function was r is equal to 2 parentheses 1 plus cosine theta, and then you square it, d theta. And now all we have to do is go ahead and integrate this by hand. If you want to check your work, you can use a calculator, but you definitely need to know how to do this by hand. So the 1/2 comes down, and when I square it, I get 4, 1 plus cosine theta squared. And then when I bring out the 4, it's going to multiply by 1/2, and you get 2 integral 0 to 2 pi. And then I'm going to work this out. And this wouldn't be so bad if I didn't have to deal with that cosine squared. So what we're going to do is, we're on the side. I'm going to take this cosine squared and I'm going to deal with it over here. So it's important that we remember this double angle formula, which is cosine 2 theta is equal to 2 cosine squared minus 1. And my goal here is to get rid of the cosine squared. So I'm going to add 1 to both sides and divide by 2. So now I can replace the cosine squared with cosine 2 theta plus 1 over 2. So my new integral becomes 2 integral 0 to 2 pi 1 plus 2 cosine of theta plus cosine 2 theta plus 1 divided by 2. So again, I'm replacing cosine squared by this bit here. And at this point, I've decided, you know what? I actually want this 2 back inside my integral, because I don't want to deal with fractions. So this becomes the integral from 0 to 2 pi, 2 plus 4 cosine theta plus cosine 2 theta plus 1. Then I just combine like terms. 4 cosine theta plus cosine 2 theta plus 3. And now that I've reached that step, all I have to do is go ahead and integrate. So 4 cosine theta just becomes 4 sine theta plus, this is going to become sine 2 theta divided by 2 because of the reverse chain rule, plus 3 theta from 0 to 2 pi. Now that's all left to do is go ahead and plug everything in. So this becomes 4 sine of 2 pi plus sine 4 pi over 2 plus 3 times 2 pi minus, this whole thing is going to go to 0. This goes to 0, and this goes to 0. So then my answer is going to be 6 pi. And that gives me the area inside of that polar curve.